welcome to this lectures on linear algebra. Last couple of lectures we have been seeing some examples about generating systems, linear independence and a basis of a vector spaces. I still want to discuss some more examples which are very much useful for applications in physics and mathematics and even computer science. So, let us continue with the next example. This example deals with what one call in physics spline functions. So, the R valued functions on R, they are functions from R to R and they are, it is a family. So, for each real number A in R, we are looking at the function f suffix a, which is defined by t goes to modulus of t minus a. So, we would like to check that these functions are linearly independent over R. So, this means, so let us try to prove this. This is really very simple proof. So, simple proof. We need to show that if, so let n is a natural number with C1 FA1 plus C2 FA2 plus Cn FAN is actually the 0 function, where C1 to Cn are real numbers and A1 to An are also real numbers. To show that these functions are linearly independent, we need to show that if a finite linear combination is 0, then each coefficient is 0. Now, we need to show C1 equal to C2 equal to Cn, all these real numbers are 0. But this function, this is left hand side is a function and it's 0 means it's a 0 function. So, this means for every t real number, when I evaluate left hand side, I get C1 FA1 t plus C2 FA2 t etc. plus Cn FAN t. This is 0. This is 0 for all t. That is the meaning of this equality. But then by definition of these functions, this is nothing but C1 mod of t minus A1 plus C2 mod of t minus A2 plus Cn mod of t minus An. This is 0 and this equality is true for all real numbers t. This is important. So, this means when you I want to keep only one term on the left hand side and shift all other terms on the other side. So, we will get C1 mod t minus A1 equal to minus, I will write summation, I is from 2 to n Ci mod of t minus Ai, and this equation is valid for all t in R. So, if you look at this equation, this on one side it is a polynomial. So, on one hand on the interval minus infinity to A2. First of all, without loss of generality, I want to assume, we may assume A1 less than A2 less than A. Otherwise, you renumber them. So, on the interval minus infinity to A2, so they are numbered like this. So, this is a real line and this is A1, this is A2, so on, they are increasing, this is AN, and so I am looking at this interval, open interval. On this interval, on one side it is a polynomial function, one hand it is a polynomial function of degree less equal to 1. And see, on the other side it is this function. So, it is clear that this is possible, only on the other side it is positive. So, this is possible only if the coefficient C1 is 0, because it is positive on this side is a polynomial of degree less equal to 1. So, this is possible only when C1 is 0. This is very easy to say, you draw. So, that means we have proved C1 is 0, and then by induction, conclude that C2 etc. all are 0. All right. So, yet another example, this example is very useful. The next example is very useful when one studies complex analysis or differential equations, and they are also used in physics. So, the next example, now let us take a subset D, let D be a subset of complex numbers. For example, you could take D equal to the unit disk. For example, you could take this equal to D, the disk, and I need to assume, which obviously this disk has this property, D has a limit point in C. We assume that D has a limit point in C. I will indicate you where do I use this property, for which, and now I consider functions. Now I look at the vector space, C vector space of complex valued functions on D. These are all maps F from D to C. F is a map. And we have noted earlier that this is a C vector space, and I want to give countably many elements here, in uncountably many elements in this vector space which are linearly independent. So, that will also, when we define the dimension etc., that will also prove that this vector space has uncountable dimension. So, the functions we consider here are the functions for each alpha in C. We are looking at the function e power alpha z. See, this is a function, this is defined from D to C. This is defined everywhere actually, but think of it as a function from D to C. See, these are functions from D to C. Is z going to e power alpha z, exponential alpha z, and I want to show you that these are linearly independent. So, we will show the family e power alpha z, alpha varies in C, is linearly independent over C. That means what? That means if a finite linear C linear combination of this function is 0 function, then the coefficient should be 0. So, suppose that we have a sum like this, a1 e power alpha 1 z plus a2 e power alpha 2 z plus an e power alpha n z. This is the 0 function. That means this equality is valid for all z in C, and this a1 to an are the coefficients which are also complex numbers, because we want to prove they are linearly independent over C, and this alpha 1 to alpha n are fixed complex numbers. What is varying is z. And now we differentiate this. Okay, first of all, note that where I am using the fact that the subset D that we have assumed that has a limit point. So, if the left hand side is a function on Z, function on D, if a function on D is 0 and D has a limit point, then it is 0 everywhere in C. So, this is very important theorem in complex analysis. So, this is, I will just note it, this is called identity theorem for analytic functions. What does it say? It says that if you have an analytic function on a domain D where D has a limit point, then it is actually the 0 function. So, by that this will be 0 for all complex numbers. So, I made a mistake here. First, to start with, it is 0 for all D, all elements in D, but because of the identity theorem for analytic functions, this equality actually holds for all Z in C. This is where we are using our assumption that D has a limit point in C. Now, when I differentiate this, what do I get? When I differentiate this, and everybody is aware that when I differentiate exponential, what is the derivative? That a1 first term, that is alpha 1 times e power alpha 1 z. This is the derivative of this term with respect to z, plus a2 alpha 2 e power alpha 2 z plus a n alpha n e power alpha n z. This is also 0 function. If a function is 0, then the derivative is also 0. This is one equation I get. On the other hand, this given equation I could have simply multiplied by alpha 1. So, if I multiplied this equation by alpha 1, what do I get? A1 alpha 1 e power z plus A2 alpha 1 e power alpha 2 z, this is alpha 1, plus so on, plus an alpha 1 e power alpha n z. So, this equation we have multiplied by alpha 1, it is 0. Now, I subtract. If I subtract, this first term will go, and then what do we get? Then we will get summation from 2, I equal to 2 to n we get an equation that is ai alpha I minus alpha 1 e power alpha I z, this is 0. So, we have now a new equation, and this is true for all z in C. So, we have reduced the length of this linear combination. So, by induction the result follows. By induction we get these coefficients 0, but alpha i's are distinct because we have to take different functions. Therefore, from here you conclude these coefficients are 0, but alpha I cannot be alpha 1, therefore, ai's are 0 for all I equal to 2 onwards, and once that is 0, then you get only one equation which is 0. So, exponential function is never 0. So, a1 is also 0, and then a1 is 0 because exponential function is never 0. Okay, so that concludes the proof of this. Okay, now one more thing I will mention, but I will not check in detail, but the proofs of these following two assertions are similar to that of the earlier two examples. So, the next one I will just mention them, they are very useful for the solutions of differential equations. It says that again which functions. So, again we have the assumption now D is a subset of the complex numbers minus the negative real axis. So, here we have a complex plane, but I am omitting this negative real axis. This is omitted because this is done so because I need, we are considering these functions z power alpha. These are functions for each alpha in C, alpha in not in C, alpha in D. I am considering these functions z power alpha, which are functions from D to C. Remember the definition z power alpha, the definition of z power alpha makes sense only when, this is the definition, which is e power z log of alpha. This makes sense only when alpha has no, alpha is not a negative real number because log does not make sense. So, for that reason we have to take a subset D of the complex numbers minus this negative real axis, and also we need to assume now D as a limit point. In this, in C minus this negative real axis. This assumption is like another earlier example. We have used identity theorem for analytic function. That means if an analytic function is 0 on a subset who has a limit point, then analytic function is 0 everywhere. So then the family, this family, so then z power alpha, alpha varies in complex numbers, this is linearly independent over C. It is the idea of the proof is similar, so I will omit it. But now I want to combine this example and earlier example. So combination becomes so the combination is if I take the functions again with the same assumptions, D is a subset of real numbers, the complex numbers with D as a limit point. These are the assumptions. In C. Then I consider the function z power n e power alpha z. Alpha is varying in complex numbers, or you can take complex numbers, and this n is varying in natural numbers. So now I didn't have to bother about omitting this negative part of the real axis because I only took the integers. Natural numbers, not even integers. So they are only in the this side, and I have these product functions. This family is linearly independent over C. Proof is again earlier two examples combined. These functions are also called quasi polynomials. They are useful in describing the solutions of the differential equation with constant coefficients. I will not go into this right now. Now the next one is also very important for next example is also very important for when more than one scalar field is involved. So typically let us say suppose V is a complex vector space, V is a C vector space. But you see this field C has a subfield R. R, the field of real numbers, is a subfield. And by very definition of C, 1 comma I, they are elements in C and they form a R basis of C. This is clear because we know that every complex number Z we can write in uniquely as x plus iy, where x and y are uniquely determined real numbers. And this I is a, if you draw a picture, it is like this. So this is I. This is y axis is called the imaginary axis. So, and 1 is here. So, these two elements form a R basis of C. So, if you start with a vector space over C, that is also, then V is also a real vector space. R vector space by restriction of scalars. By restrictions of scalars. And if now if you give a C vector space basis of V, then how do we extract, how do we find an R vector space basis of C, V? This is the problem that is addressed in this example. So, suppose Vj, j in j is a C basis of V. Now, it is more than one field is involved. So, it will be very essential to write what basis and linearly independent or what, etc., etc. Then I want to check, then Vj and I times Vj, j is varying in j, is a R basis of V. So, remember this I is the, this is also called imaginary, complex imaginary number. No? So, this is that I. So, I have avoided using indices I. No, so this means in particular if a C vector space has a basis consisting of n elements, then its R basis will consist of 2n elements. So, the dimension will become 2 times. So, this will mean that dimension of V as a C vector space and dimension of V as a R vector space, they are related by 1 is 2 times the other. This I will mention again when I have introduced actually the dimension, which is in the next lectures. So, what do we have to prove, to check? We need to check two things. We need to check that every element of V is a combination of these guys with real coefficients, and what is given to us is every element x of V, we can write it as a combination with coefficients in complex numbers. So, every x in V, we can write it as, I do not want to use A. So, Zj times Vj, j in j, where all but finitely many Zj's are non-zero. So, Zj belongs to C power round bracket j, j in j. This is what we have given, because this generates V as a C vector space. And now I want to check that this generate V as a R vector space. So, that means I should have a expression for x is this. I should have expression for x in terms of Vj's, but the coefficient in terms of Vj's and I times Vj's, so that the coefficients allowed are only real numbers. But this is very simple, because each Zj is a complex number. So, each Zj I can write it as xj plus iyj, where xj, yj's are real numbers. So, just plug it in there and separate it out. So, you will get j in j, xj plus iyj zj, vj, and if almost all zj's are 0, then also almost all xj's and yj's will also be 0. So it will also be clear that xj belongs to R power round bracket j and yj belong to R power round bracket j. And when you expand this becomes summation xj vj plus summation yj, and that I will push it inside I vj. So we managed to check that this is the generating system for V over R. Now we also have to check that they are linearly independent over R, but we have given this is linearly independent over R, and the trick is the same. So if some linear combination is 0 with real coefficients, then do each complex number, write it like this, or each combine these two real numbers with this and we get a complex number, so it will be 0. So I will stop, and we will continue in the next half more. I will now try to prove that every vector space has a basis, and then the next step will be any two bases of a vector space have the same number of elements, and that will give us a concept of a dimension. Thank you.